This is the third lecture of our course. Today we'll talk about one more sorting algorithm. We'll talk about Quicksort algorithm. And Quicksort algorithm is a little bit different from what we learned on the first lecture. It's different because it is randomized. So first we'll talk about what is a randomized algorithm and how to measure the randomized algorithm time. So what is the randomized algorithm? What usually happens? Usually you have some algorithm, like we did on the first lecture. It has some input data and some output data. So you have some input here. Like for sorting algorithm, you have some array for input and some output. Again, in sorting algorithm, you input the array and you output the same array in the sorted order. What happens when you have a randomized algorithm? You have another source of input. So you have another input here. And that input gives you some random numbers. I don't know why it's not working for you. That's sad. Maybe you have some problem with Twitch. I don't know. Twitch is strange. Okay. You can watch it in the recorded version, but it's sad you can't watch it live. Okay. So you have some input data, some output data, and additional input source of input, which gives you some random numbers. And the interesting thing is that random data may help you to solve the problem faster. So sometimes it happens that these random numbers can help you to solve the problem. For example, so we will learn the first randomized algorithm. It is Quicksort algorithm. So how the Quicksort algorithm works? Imagine you have some array. So we have some array A. And we want to sort this array in increasing order. So what we can do? We will do the following. We will pick the random element of this array. Let's pick some element x. Let's see, random. And then we'll split the array into parts. Left part and right part. In the left part, we will put all elements which are less than x. So we'll put all elements less than x in the left part. And in the right part, we'll put all elements which are bigger than n. So greater or equal than x. Let's see. I claim that we can split array into two parts in linear time. So how to split array A into parts in linear time? Well, we simply go from left to right and just look on each element. We take this element, see if this element is less than x, we put it in the left part. If it is greater or equal than x, we put it in the right part. So in linear time, we will get these two arrays. Cool. Now, what we can do? We can call the same algorithm recursively for these both parts. So we call it again for this part. Again, we pick some random element, split into two parts. Again, pick some random element, split it into parts, and so on. Until we have an array of size 1. When we have an array of size 1, it's already sorted. That's all. That's how the Quicksort algorithm works. Should we write the code? No, let's write the code. It will be simple. Let's upgrade it a little bit. Instead of having new arrays each time, we can upgrade it by using the same array for these two halves. So instead of splitting array into two arrays, we will use the same array, but just split it in between. So we'll use the same array A, just put the elements less than x in the left half of this array, and elements greater or equal to x in the right part of this array. And then call the same procedure for these both parts. If we pick elements random, so sometimes we can pick the bad element. So this element is not always a good element. So in this picture we split array almost in halves, but in reality you may pick some wrong element. So the array will be split not in equal parts. So it may happen. It's more like merge sort, but in merge sort we first split array, then merge them together, and here we just split arrays and then in two halves, which are first elements are less than second elements, and then call the recursive procedure. So it's like merge procedure in reverse. So in merge sort we first split array, call recursive calls, and then merge these two arrays into one, and here we just pick the element, split arrays split array in two parts, and then call the recursive procedure for this part. Yes, we can pick the same element several times. That's fine. Yes, we'll discuss why is it fast. We will discuss a little bit later. So let's just write the code first. I like to write the code. So every time you call the recursive procedure, so every time you give the recursive procedure some segment of the array. So the segment is defined by its borders. So we'll have left borders L and right borders R. So we need to sort all elements from L to R minus 1. Nice. Let's go. So first, if the size of this part is less or equal than 1, so if R minus L is less or equal than 1, then we have either empty array or array of size 1. So it's already sorted. So we just return. If the size of array is at least 2, then we pick the random element from L to R minus 1. Asks about home task you can ask in comments on Code Forces. I think it's better to discuss it there. Yeah. But you can ask it now. Maybe someone will answer that. Cool. So we pick the random element, and now we need to split array into two parts. So how can we do it? We'll go from left to right and maintain the following property. We go from left to right. And each time we'll split this prefix into two parts. So these elements will be less than x, and these elements will be greater than x. So this will be from L to M, and this is R, this is I. So we go from left to right in this variable I, take next element, this element. If this element is greater or equal than x, then it stays in place. If it is less than x, Then we'll split this element to this element and increase the variable m. So let's say we go from so let's say m equals to L, then go for I from L to R minus 1. Take next element, see if this element is less than x. Then we move this element to position m. Alright, so we swap element position m and increase m. That's all a splitting procedure. Go from left to right, take the element, put it here. So in the end, we will have the array split it into two parts. So we have these elements less than x, these elements greater or equal than x. This is L, this is M, this is R. And now we simply call the same procedure twice. So we call sort from L to M and sort from M to R. That's basically all implementation of the quicksort. It's not the best implementation. Now we'll discuss why it's not the best implementation, but it's good enough. Now, did anyone find something strange about this procedure? This procedure sometimes doesn't work. So sometimes, for some arrays, we have very strange situations. Can you find out what is? It's for so many insertions. Why is it not suitable? It's not snap, it's swap. Stop. Yes, the biggest problem of this implementation is that it doesn't work when you have equal elements. So if you have several equal elements in your array, 2, and 2. Simply swaps two elements. So we take elements AI and elements AM, and we just swap these two elements. These elements go here. Can I illustrate them? Okay, let's illustrate it on example. So let's have some array. Let's have array. Let's say 3, 5, 2, 6, 4, and let's say x equal to, I don't know, 5. So what happens? We have L here, M here, and R here. Now we go from left to right. Each time we take element, if it is less than x, then we swap it to position M. So now M equal to L, so it stays in place. So this element is less than x. Now we move to the next element. See if this element is not less than x. So it stays in the same place. So this element is greater than x. And M is here. Now we take the next element. See, this element is less than x. So we swap this element to the last element here. So we swap these two elements. 2 is here, 5 is here. Now we have two elements. These two elements are less than x, and this element is greater or equal to x. And M is moved to the right. And so on. We take the next element, see if this element is greater or equal than x, then it stays in the same place, so these elements are greater than equal to x. Now we take next element, if it is less than x, and we swap it with position m. So we swap these two elements. 4 goes here, 5 goes here, move m to the right, and now in the end we have these 3 elements less than x and these 2 elements greater or equal to x. That's all. No, I will not have streams in Spanish. Sorry. It actually will be cool to learn Spanish, I think, but not this year. This year was recording streams in English. Maybe later. Cool. So again, what is the problem? The problem is when you have several elements of the problem is when you have several equal elements. So if you end up in the following situation, so you have L here, R here. So you pick a random element, so all elements are equal, so you pick x equal to 2. Now you try to split arrays into parts, elements less than 2 and elements greater than 2. So you have no elements less than 2, so you have empty set of elements less than x and all elements greater or equal to x. You call the same procedure, you have the same array. So each time you have the same array. You cannot split these elements into 2 groups because they are all equal. So how can we improve this procedure? How can we improve it to be able to solve problems like this when you have equal elements? Just check if it's actually yeah, that's one solution. You can check that all elements are equal, but it's not the best solution. Because if all elements are equal but one is different, like this, you have many 2's but one 1's. Okay, there are different ways how to solve this. One of the simple way to solve this is to split array not in 2 parts but in 3 parts. You can split array in 3 parts. You can have elements less than x here, equal to x here, and greater than x here. So you split array into 3 parts, and then call the recursive procedure for this house. So elements equal to x stays in place. So we only need to sort these 2 parts of the array. Okay, that's one of the way to solve this problem. Nice. That's all. That's how the quicksort algorithm works. Now, let's think about how to measure its time complexity. So on the first lecture, we was talking about time complexity, and we decided that we will only learn how to measure time complexity in the worst case. So each time when we calculate the time complexity of the algorithm, we'll find the worst possible case and calculate the number of operations in the worst possible case. So what is the worst possible case for this algorithm? What can go wrong? So let's say we have array A. What element can we pick that will be the worst possible random element? A0. A0 may be a good element. Yeah, the problem is when you pick the element which is minimum possible or maximal possible. So if you pick minimal possible element, so if each time you pick as x the minimal element, so you split array like minimal element and all other elements. And again, you minimal element and all other elements, and so on. So every time you split the array in two like very unequal parts. What will be the time complexity of this algorithm in this case? Yes, today is only English lecture. Yeah, time complexity will be n squared. Again, like we discussed on the first lecture. Here we spend n time, spend n minus 1 here, n minus 2 here, and so on. So this total number of operations will be big O of n squared. Cool. And actually, this implementation may go even worse. So in this implementation, we may have even worse situation. So what happened in this implementation if we pick a minimal element as x? Very strange thing will happen. So in this implementation, if we pick minimal element as x, we'll split the array into two parts. So we have elements less than x and greater or equal than x. But x is the minimal element. So we have empty array here and all elements in the right part. So each time the size of array is not decreasing. So each time you have array of size n. So the total number of operations will be infinite. So this procedure will infinitely call itself recursively. So the worst possible case may be infinite. So sometimes this algorithm just doesn't finish. Is it a problem? No. It looks like a slightly major problem, but actually it's not. Why it's not a big problem? Because we pick a random element, and the probability that each time we'll pick the minimal element is very small. Actually, it's infinitely small. So if you pick the first element on each iteration infinitely, the probability of this iteration is 0. Quicksort is actually pretty quick. Yes, it's called quicksort because it's pretty quick comparing to merge sort and especially comparing to heap sort. We'll talk about this little bit later. So, in worst case, this procedure may work infinitely. And if you fix it like we did, so if you pick the element equal to x here and greater than x here, then time complexity in the worst case will be n squared. Nice. So, to measure the time complexity of the randomized algorithm, we will use slightly different technique because it's randomized. So, to measure the complexity of the randomized algorithm, we will measure not the worst case type complexity, but the mathematical mean of the time complexity. We'll measure not the number of operations, because number of operations is some random function. So we'll calculate the estimated meaning of this random function. So mathematical mean of the number of operations which algorithm will take. And this mathematical average is calculated as follows. So it's just like let's say it's just sum of x multiplied by probability that time equal to x for all x. And it helps a lot because the probability that your algorithm works very slow is very small. So if you have n squared iterations, it means that each time you pick the minimal element, the probability that each time you will pick the minimal element is very small. So big as your array, the smaller is the probability. So when we calculate, when we multiply this big number of iterations by the small probability, we will get something good. Cool. Now, let's prove that for Quicksort algorithm, the mathematical average of the time is actually n log n. How can we prove this? Let's see. So we have array A. Each time we pick some random element, split array into two parts. Left part, right. Should you believe in this formula? No, this is the standard formula for mathematical. I mean. Okay. So let's calculate the mathematical average of this time complexity. So we have some array. We pick some random element. So what we need to see, the probability that we pick each element is, so for each element x, the probability that we pick element x is 1 divided by n, right? So let's see, if we pick, let's say, k elements to the left part, then time complexity will be, so we need to split elements into two parts in linear time, and then we make two recursive calls here. First recursive call is t of k, and second recursive call is t of n minus k. Now, this k is random, so we can pick all elements with equal probability. So to calculate the estimated value of t, we actually need to find the sum of this multiplied by 1 over n for all k from 0 to n minus 1. Yeah, куда там? Yeah, this is estimated everywhere. I just remove this. So every array is an estimated value of the time. Now, how can we solve this? The easiest way to solve this is by doing the following. So, let's say that if we pick element from this middle third, so if we pick one of the elements from this middle third of the elements, it is good. So if we pick one of the elements in the middle of the array, so it's n over 3 elements here, then we make a good split. So we'll split elements in not half, but close. The sizes of both parts will be close to each other. Cool. So what is the probability it will pick one element from this group? It is 1/3. Let's remove this. So with probability 1/3, we will pick one of the elements from this group. If we pick one of the elements in this group, then k will be from n over 3 to n over 3. So size of each of these parts will be no more than 2/3 of n. So this sum will be no more, let's see, this no more, then t of n over 3 plus t to n. So this happens if you pick one of the elements from this middle group. And if you pick one of the elements from this outer group, you will split the array in some not very equal groups. So if you pick one element here, you will split your array very badly. So you will split it somehow like this. We'll say this is the bad split. So in the bad case, which happens in 2/3 of the case, you will split something like that. And we will say the worst possible case when we split elements into groups like 1 and n minus 1. So we'll just, it's no more than, let's say, t of n. So this is the good split, let's say. This is the good split. This is the bad split. I lost plus n. Plus n. So this happens when you pick one of the elements in the middle group. And this happens when you pick one element in these groups. So it happens with probability 1/3. This happens with probability 2/3. Now let's just use this formula. So what happens, we move this to the left. So we had 1/3 here. Just remove this. Let's multiply everything by 3. So we have t of n no more than 3n plus t of n over 3 plus t of 2n over 3. Something like this. And now we just prove by induction that this actually is n log n. Let's prove that t of n is no more than c multiplied by n log n. It's like we did on the first lecture. So we have n over 3 is smaller than 3. This is smaller than n. So we use this formula for these two parts. So we'll have something like t of n is no more than 3n plus cn over 3 log n over 3 plus c2n over 3 log 2n over 3. And now just, well, like we did in the first lecture, we use this logarithm. Cn, logarithm of n over 3 is log n minus log 3. Here we have log n minus log 3 over 2. So in the end we'll have something like it's too much mathematics for one lecture actually. That'll be the last formula in this lecture, I promise. So we have this. Let's just remove n from this. So we have n multiplied by 3 plus here we have cn over 3 multiplied by log n. So we have plus log n plus plus this c2n over 3 multiplied by log n, and then minus this and minus this. minus c n over 3 multiplied by log. No, I removed n. Yes, I moved n here, so it's 1 here. Sorry. Minus c multiplied by log 3, right? And minus c over 2 by 3 logarithm of 3 over 2. Whew. Yeah, looks fine. So now we simply move these two close together. So the sum of these two is c multiplied by log n. So we have this equal to cn log n plus something like n multiplied 3 minus this part. So this c of 3 log 3 minus c to third log 3. And now we just pick the big value of c. So we say if c is big enough, so if c is big, then this is less than 0. So this is less or equal than c n log n. Whew. Master theorem is, you can use something like master theorem because you have two segments here. So you have two recursive calls of different argument. So master theorem is not very good for this. Okay, it's good enough. It's not 7. Where you can see 7? No, it's 3. Where do you see 7? It's 2. And this is 2. My writing is not very good. It's not a big deal. So you have some constants here. So you have some constant here, some constant value here. So if c is big enough, then this bracket is less than 0. Good. Another maybe more natural way to think about this is like this. So you may think about this algorithm like this. So what actually happens? Let's see, we have array A. Let's say if we take one of the elements from the middle group by random, so we pick some random element. Maybe we'll pick a good element. Let's say if we pick element from this middle group, it is a good way. So this happens in every third case. So every third time we pick element from array, it belongs to this middle group. Let's say we pick element from this group. And when we pick element from this middle group, we'll split array into two parts, and both parts will have size no more than 2/3 of n. So every third split will decrease the size of the array by at least 2/3. So the depth of the recursion will be again logarithmic. So you have this big array. Now, after about 3 random picks, you will split arrays into two parts. So each part will be at most 2/3 of n. Now again, you make three wrong picks, and then you make a good pick. Next, again, you take this part, and again, after about 3 picks, so you have some bad picks, and then you have good picks. So you pick element from here. You split element in, and so on. So each time, after some small number of picks, about 3 picks, you will have a good split. So some splits will be good, and each good split will decrease the size of array by some constant factor. So the depth of this recursion will be logarithmic. It's actually, the depth of this recursion will be about, let's say, 3 multiplied by logarithm of n base 3. Something like that. So that's more intuitive way to think about this. And if the depth of the recursion is logarithmic, then the total time complexity will be n log n, because on each layer of the recursion, the total time complexity of all the recursive calls will be n, like in merge sort. Cool. Do we have enough time? Yeah, we have enough time. So let's talk about the following. What happens in practice? So this Quicksort is quick because it's relatively good in practice. So what might happen in practice? In practice, what happens? You pick random element. Sometimes you split elements. You split array in a good way. Sometimes you split array in a bad way. To increase the efficiency, to decrease this constant, we can find the way to pick the better element with better probability. It will not be asymptotically better, but it will decrease this constant factor. In practice, you not only think about the asymptotics, but also you think about the constant factor. So in practice, you may want to decrease this constant factor. How can you do it? You can pick the element in the middle with better probability. So how to pick elements from the middle group with bigger probability? One of the ways to do it is to pick not one element, but let's say 3 elements. Let's pick 3 random elements from the array. Like 1 element, 2 elements, and 3 elements. Then look on these 3 elements and pick the middle one as x. So we sort these 3 elements, random elements, and pick the middle one. And if you pick 3 elements and take the median, you'll have the better probability that this element will be closer to the center of the array. So, and if this probability is bigger, then this constant factor will be smaller, so the total time complexity will be slightly smaller. It will still be n log n, but this constant will be smaller. Alternatively, you can pick not 3 elements, but let's say 5 elements. You can pick 5 elements and pick the middle one. You will have slightly better performance and so on. I think it's fine. So this is how you measure the time complexity of a randomized algorithm and how to measure time complexity of the Quicksort algorithm. One of the things I want to notice is that we measure the time complexity in the worst case, but this worst case is all over the inputs. So we take the worst possible input. Let's say input is worst case, but random is random. So we take each input and calculate the average time complexity for this input, and then take the worst possible input. So we take the input which have the worst possible average time complexity. So again, we measure the time complexity in the worst case, but the worst case is not over these inputs, not over these random values. So random values are some random values. And there is better time complexity. Can we use the Gaussian probability? The problem, you can use Gaussian probability because you want this probability over the sorted array, but you didn't sort array. So you have this array not in sorted order, but in some random order. So you can't pick the middle element with Gaussian probability. Basically, when you given some array, all elements are equal for you. You don't know any relations between these 2 elements. So it's strange to pick some non-uniform distribution. So if you pick elements of different probabilities, in the worst case, the wrong element will be picked with a bigger probability. So the best thing you can do is just pick all elements with equal probabilities. Cool. So let's move next. Next, we'll move not to the sorting algorithm, but we'll discuss something similar to the sorting algorithm. We will discuss the order statistics problem. Statistics. Not sure about English. So what is the problem? Let's just clear. So we have the following problem. You're given some array, and you need to find the element which will be given index, array and index k. You need to find the element of index k in the sorted array. So if you sort this array, and pick the element index k, that is the element you want to find. So this is the case statistics. That is Quicksort, I think. English is difficult. I think it's always statistics. Yep. Fine. Good enough. So you want to find this element in the sorted array. Good. What is the obvious solution? Obvious solution is just to sort the array and then pick the element. That will cost you n log n time. Yeah. Just sort and pick. And the interesting fact is that you can do it actually faster. You can find the element at index k without sorting the whole array. So you can find this element and do not sort the whole array. Good. Now we'll discuss the randomized algorithm, which works faster than this time complexity. The algorithm works like this. So you have the array A. Again, like in Quicksort algorithm, let's pick some random element. We pick some random element x. Pick this element x and split it into two parts. So we'll split it less than x, greater than equal to x. And now let's look, where is the element of index k? So if k is less than the size of the left part, then we only need the left part of it. So if k is here, then we don't need these elements in the right part. We only need these elements. So we call the same recursive procedure, but only for this left part of the array. So again, we take this. Now again, we pick some random elements, split it into two halves. Let's say this and this. See where is element k, pick this part, again split it, pick one part, again split, pick one part, and so on. In the end, we have only one element in this array. That's strange. What? For some reason, Twitch is not working for someone. I don't know. Maybe I have some wrong settings. I need to investigate this. I don't know why. That's all. That's how the algorithm works. Each time you pick the random element, split the array into two parts, then pick one of the parts which contains the element k, and so on. In the end, you have the array of size 1. This small array contains this element you want to find. Should write the code? Well, let's write the code. Again, let's have a recursive procedure. Let's say find. Again, we have elements from L to R, and we need to find element K. Yes, and we will maintain the invariant that K is between L and R. So K is greater or equal than L and less than R. Now we see if this array has size 1, if R minus R equal to 1, then we return element K. If it is more than 1, we will split this array. So we say X is the random element. Now again, we do the same. We make this split. So we split elements from L to M, this to R. Should I write it again? Okay, let's do it again. So again, we have M equal to L for I from L to R minus 1. If element is less than X, we swap and increase M. So we split array into two parts, less than X and greater than X. Now we see which part contain element K. So if K is less than M, then we make recursive call for the left part. And if it's greater or equal to M, then we make recursive call for this right part. That's all. That's all about. That's the whole algorithm. What is the difference from the previous algorithm? So it looks almost the same as the quicksort algorithm. Yeah? So quicksort algorithm has time complexity n log n. And I claim that this algorithm has better time complexity. Why it is different from the quicksort algorithm? What is the key difference? No, it's operations is almost so this part is actually equal to the same. We have the same part in the quicksort algorithm. We just split array into two parts. But it has one big difference from the quicksort algorithm. Yeah. The key difference is we make only one recursive call. In quicksort, we make two recursive calls. We make recursive calls for the left part and recursive calls to the right part. Here we make only one recursive calls. We go to the left part or to the right part. So we have this recursive call or this recursive calls. We never have these two recursive calls at the same time. That's better. So what will happen? So why time complexity will be better? So what happens? We pick a random element and then pick one of the two halves. So now again, every third time we'll have good split, and the good split will decrease the size of array to like 2/3 of n. So we have total time complexity will be n on the first iteration. Then we make a good split. We have like 2/3 of n. Then after another good split, we have 4/9 of n plus and so on. And what is the sum of this series? Yeah, that's all the same. So we have only one recursive call. So each time we have not the sum of these recursive calls, but only one recursive call. And one recursive call costs you 2/3 of n. So this sum equals to 3n. Good. So total time complexity will be linear. That's all. That's how you find the element in a sorted order without sorting the whole array. So you just split the array and then just remove one of the parts because you don't need to sort these elements and only make recursive call in one half and so on. So the total time complexity will be linear. That's all. Good. Any more questions by now? Yes, I will upload it to YouTube, as always. Okay. And the final one. One more algorithm. Why do people use randomized algorithm? There are many reasons. First reason is these algorithms sometimes are faster than the usual algorithms. So, for example, this is Quicksort. I already erased this. Quicksort algorithm is called quick because it's actually pretty quick comparing to, for example, heap sort. Because heap sort just pick random elements and Quicksort goes from left to right and it's good in caching and so on. I'll do it in a second. So sometimes randomized algorithms have better asymptotic time complexity. It happens. For some problems, we know the first randomized algorithm, but we don't know the first determined algorithm. So sometimes scientists have found some good randomized algorithm, but we didn't found the good determined algorithm. That happens. So the next the final thing we will do in this lecture, we will show how to achieve the same asymptotics using the determined algorithm without any randomization. They asked me to repeat this. Let's repeat this once again. So what happens here? We pick the random element and split array into two parts. And with probability about 1/3, we will split the array into parts in such a way that both parts will have size at most 2/3 of n. So the probability of this is about 1/3. So after you have the size decreased to 2/3 of n, again you will have some random pick, and after some random picks you will have 4/9 of n. And because you have only one recursive call here, the total time complexity will be sum of this series. So the sum of the series is 3n, so it's linear. So it's just sum of some geometrical progression. This happens a lot in computer science. You have some algorithm which decreases the size of input by some constant factor, and the sum of all these recursive calls will be linear. It happens not only in this algorithm, it happens a lot actually. When you have some linear algorithm which works like this, you have some big input, then you do some magic stuff and decrease the size of input by constant factor. So and call the same algorithm for this smaller input. So the total time complexity will be linear in this case. Good. So again, the final thing. We will show how to achieve the same time complexity using determined algorithm. Good. Let's just erase this. What is the idea? So, why do we need randomization? Because we want to pick some good element x. Okay? So the idea is algorithm to pick some good element x and then split array into two parts. And to pick the good element x, we just pick the random element. Random element will be good with some good probability. Let's try to pick the good element with probability 1. Just like find the determined way to pick the good element. Yeah, cool. This is the algorithm of 5 people. It's of Bloom, Floyd, Pratt, Rivest, and Trajan. Bloom, Floyd. I think like this. Pratt, Rivest, and Trajan. So we need like 5 people to invent this algorithm. Cool. How the algorithm works? So, what is the idea? We do everything the same, but they pick this element x not in random way, but in determined way. So we need to find determined way to find the good element x. Somehow. Everything else will be the same. So how to pick good element x? You do it in the following way. You take the array A and you split it into groups of 5 elements. So you have n over 5 groups, blocks. Let's draw it like this. It's easier to show it when you have like this. So we have these are blocks. So each block has size 5, and you have n over 5 blocks. Blocks. This is array A. Now, what you can do? You can find the median element in each block. So you take each block, sort elements inside this block, and take the median element. So you take this median element. This element is, let's say, greater than this element and smaller than this element. So this is the median element from these 5 elements. Okay? And you do it in each group. So in each block, you sort these 5 elements and take the middle one. Let's notice we can do this in linear time. So in linear time we can split array into blocks, and in linear time we can find the median in each group. Yeah? Because the size of group is constant, so we can just sort this element using any sorting algorithm, and then take the middle element. It will cost you some n multiplied by the size of the block. Nice. And then we'll do the following. We'll take these median elements from each block and find this median of all medians. So we'll take these elements and find the median of these elements. Again, we have 8 blocks. Let's have 9 blocks. So if we have 9 blocks, we need to find this element. And this element will be x. That's the whole algorithm. Again, what we do? We take the array A, split it into blocks of size 5, then find the median in each block, and then find the median of these medians, and say that this median of medians is x. And now we do everything the same. That's all. That's the whole algorithm. Yes, that's a good question. To find this median of medians, we need to sort these elements. But actually, we don't need to sort them. We only need to find the median. And to find the median element, we can use the same algorithm recursively. So what can we do? Let's see, T of n. First, we spend some linear time to make all this. So just to find all these medians and so on, split everything. Now we take these median elements and call the same algorithm to find the median of all these medians. So we'll spend T of n over 5L time. This is to find the median element. No, if we use quicksort here, we will spend n log n time. We don't want to spend n log n time. Yeah, these all people are very famous one. Yeah, these all these names may be familiar for you. Yeah. Good. Now we make the recursive call to find this median element. And now we split array into two parts and make recursive call in the part which contain element k. So what may be the size of this array? What may be the maximal size of this group? So make another recursive call of this part which contains element k. Let's see. For example, we pick the left part. So we pick the left part. These are elements less than x. What will be the maximal number of elements less than x in this array? Let's see. Where are the elements less than x? So these elements are less than x. And these elements are less than these elements, and they are less than x. So these elements are also less than x. What other elements can be less than x? Well, actually, also these elements can be less than x, because if we have x here, here we have some elements less than x, and here some elements more than this element. So these elements also could be less than x. So these elements also could be less than x. And the same thing here. So these are some elements which are less to some elements which are greater than x. So these elements also can be less than x. And this all elements here cannot be less than x, because these elements are greater than x, and these elements in the bottom are greater than these elements. So each element in this part of this rectangle are greater than x. So these are all the elements which could be possibly less than x. What is the total number of these elements? So we pick all elements here, so over 2 here, and like 2 of the 5 in each block here. So we have, let's see, we have half of elements here, and we have half of elements, and from each block we have 2 of 5 elements. So it's 2 of 5 elements, and over 2. Let's see, this is n over 5 plus n over 2. It's 7n over 10. So the maximal possible size of this part is 7n over 10. So that's all. And now I claim that if you have this recurrent formula, then the time complexity is linear. Let's prove this. Well, again, how to prove this? We use mathematical induction. I promised it was the last formulas, but okay, this is the last formulas. So we want to prove that t of n is no more than c multiplied by n. Now we use this. We use t of n is no more than n plus c n over 5 plus c 7n over 10. I'll just say n here. What we have here, we have 1 plus c multiplied by n over 5 plus c over n is 9n, no, we removed 1n here, and over 10, right? Looks fine. Yes, yeah, no, we use the same procedure for every recursive call. So every time on each recursive call, we use this procedure. We split the array into blocks, find median of medians, and so on. This happens in each recursive call. So here we have the same recursive call, and here we have the same recursive call. And finally, now what we need to do, we need to find c such that this should be less or equal than c multiplied by n. So let's just divide it by n. We have 1 plus 10 of c not equal than c. Just move this to the right. We have c over 10 here. Multiply this by 10. So this is true. Then c is at least 10. Now we pick c equal to 10, and we have the correct proof. And that's all. Again, the algorithm is basically the same as the randomized one. The only difference is that we pick the element not in random fashion, but in deterministic fashion. So we find the median of median, and we claim that this element is the good divider. So we pick this element x, divide the array using this element x, and then each half will be at most 7n over 10. So total time complexity will be linear. That's all. Okay, I think it's all for today. Thank you for joining me today. Thank you for watching.